linear optical spectroscopy. If you are looking at optics in the linear regime and you ignore any polarization effects, there are two quantities that completely describe the behavior of a given material sample, being the absorption of the sample at each frequency and the phase shift at each frequency. They're not independent parameters. There's a causal constraint called the Kramer-Kronig relations that tell you if you know the absorption at every frequency, you can determine the phase shift at any frequency and vice versa. Note that you do have to know the behavior over all frequencies. In practice, people use these quite often, but they measure only a finite range of frequencies and then use some model for how the system behaves at low and high frequencies to sort of infer the rest of the spectrum. Instead, it's better if you can just directly measure both absorption and phase. Then you don't need any model. You can determine the exact response of the system without making any assumptions. I'll talk about absorption spectroscopy on its own first. The classical solution to this is pretty simple. You have an unknown sample, you send light into it, you collect light out of it, and the ratio of ingoing photons to outgoing photons tells you what the absorption is. Outgoing photons you can measure exactly. If you just put a photon number resolving detector after your sample, you can determine the precise number of photons that exit it. For incoming photons, the situation's a little bit different. In that case, no matter how well you characterize your light source, if you're using classical light, and I'm using the word classical here in the same sense as Anel yesterday with respect to the p distribution, any classical source of light is going to be limited by shot noise. That's just because classical sources of light do not produce a photon number eigenstate. So the relative error in the number of input photons, if you do not characterize it beforehand, is going to be bounded by 1 over root n. If you want to make a very precise measurement of absorption, you need a large number of photons, and then that relative error goes to 0. In practice, a lot of material samples, especially things like single molecules, are limited in the number of photons that you can expose them to before they will be irreversibly damaged by your incident light. For a typical organic molecule, that's about 100,000 photons before it goes through some irreversible change. So if you have a bound on the number of photons you can expose your sample to, and you have a bound on the precision with which you can measure absorption for a given number of photons, you have a hard limit in classical spectroscopy as to how well you can do in this situation. If we're looking at non-classical sources of light, then the situation's a little bit different. David Klitschko addressed this quite a while ago. His solution is to prepare light using photon pairs. The modern way of doing that is with parametric down conversion. You send one pump photon into a nonlinear crystal. It splits into 2 lower energy photons. This conserves energy and momentum in the optical field. And so you have tight correlations between the frequencies of the 2 emitted photons and their direction of propagation. In particular, for Klitschko's method here, if you know the number of photons that are emerging in one of the 2 beams, you know exactly the number of photons in the other beam as well, because they are always emitted in pairs. So in this case, you can measure one of the arms leaving this crystal. I'll call it the herald. That will tell you the number of photons incident on the sample in the other arm. Now you know exactly what the input number of photons is, the output number of photons, and you can get around the shot noise limit. I'm not going to talk about this scheme too much, but there's a experimental demonstration recently where they do show that you get lower noise for the same number of incident photons. Now, if we turn to amplitude and phase spectroscopy, there's a classical solution for this as well. You build a standard Mach-Zehnder interferometer, stick the sample in one of the arms. The intensity coming through the interferometer is split evenly between the 2 arms here. Half of the light goes through the sample. So when you insert the sample, there will be a decrease in the total number of photons leaving the interferometer. just due to absorption in that arm. The phase shift will show up as a difference in the intensity leaving each of the two ports in the final beam splitter there. So if you look at the sum of the intensities leaving the beam splitter, you know the absorption, look at the difference, you know the phase. This is where our work comes in. So what we're trying to do is use a heralded method similar to Klitschko's idea. However, we're going to build it into a type of optical interferometer that also allows us to extract the phase of the sample as well. I'll talk about the type of interference that we use in a second, but before we go any further, there's a very basic constraint on what kind of light you can use as your probe state here. If you have a separable state of your signal and herald photons, then any phase shift you pick up is going to be a global phase. If you want to measure what the phase shift is, you have to use a entangled state of your signal and herald so that there's a relative phase shift that you can pick up. So the type of interferometry that we do is a little bit different than standard optical interferometry. The typical classical interference for optics is single photon interference. What we do here is two photon Ou-Mandel interference. The simplest picture of this is if you send two photons into opposite input ports of a beam splitter, there are four different outputs or outcomes that can happen after they scatter at the beam splitter. In two of these outcomes, one of the photons will reflect and one will transmit so that they both leave via the same output port. The other two outcomes here are outcomes in which they either both transmit or both reflect. If you're looking at distinguishable photons, that's all there is to it. If you have a 50-50 beam splitter, each of those four outcomes occurs with a 25% probability. If you do the same thing with indistinguishable photons, then the two outcomes where one photon leaves via each of the output ports, those are indistinguishable outcomes as well. You'll get interference. And because of the specifics of how optical beam splitters work, the two terms will have a pi phase shift between them and you get destructive interference. Experimentally, the way of setting this type of interferometer up is you introduce a degree of distinguishability between the photons that you can control. Typically, this is by a time delay. If you have a large time delay in one arm, they arrive at very different times at the beam splitter. They're distinguishable, and you get that background rate of 50% of the photons emerging by the same output of the beam splitter. If you change the time delay so that they arrive simultaneously, then they are indistinguishable. You see a decrease in the number of events where they leave via different output ports. And so the number of events where that happens, we'll call it coincidences, decreases to 0. So as you scan this delay, you see a dip in the number of these coincidences. If you do the same thing with frequency entangled photons, it's a little bit different. In that case, your probe state before the beam splitter, if you add a delay, you're going to have different phases accumulated by the two terms, which depend on which of the photon frequencies went through that delay. That means that you have a relative delay, or sorry, a relative phase shift between the two terms, which is the beat frequency of the two photons multiplied by the time delay. If you scan the delay after the beam splitter, you've removed any path distinguishability between the photons. You see interference between these two terms, and that interference occurs at the beat frequency. So now I can be a little bit more specific about what we do here. We send two frequency entangled photons into a Ou-Mandel interferometer. One of them passes through the sample, the other acts as a herald. If the sample absorbs the photon that passes through it, then we get a single photon emerging from the beam splitter. By detecting what the frequency of that photon is, we can infer what the frequency of the absorbed photon is just because of these tight frequency correlations. If the sample transmits its photon, we have an entangled state of the two photons arriving at the beam splitter. We get a phase-sensitive Ou-Mandel interference pattern. So we still have this heraldic process that you see in Klitschko's absorption spectroscopy, but now we also get phase as well. Experimentally, you get a setup that looks like this picture on the left here. Very briefly, we produce broadband SPDC with a bandwidth of about 150 nanometers. We split the two photons into two arms. One gets delayed, one goes through the sample, mix them at a beam splitter. To detect them, we couple these into single mode fibers. They go to a two photon spectrometer where we can identify coincidence counts, single counts, and also resolve their frequency. The way that the spectrometer works is by taking the beam out of each fiber, dispersing it on a grating, and sending it onto a single photon sensitive camera. The camera that we use is a bit special in that it can tag each incident photon with the time of arrival down to a few nanoseconds. So by looking at pairs that arrive at the camera with very similar times and with the correct frequency correlations, we can identify those photons that were produced as part of the same SPDC event and have this entangled relationship. With this system, we get a wavelength resolution of about 0.6 nanometers, 256 spectral bins, which is just limited by the camera resolution. Unfortunately, our system efficiency is quite low. We have about a 10% efficiency collecting this SPDC into the fibers. The camera itself is 10% efficient in detecting these photons. So from the crystal all the way to the detector, we have a system efficiency of about 1%. If we plot the data that we get out of the system, you get spectra that look like what I have on the left here. What I've plotted is the intensity of detected photons. I'm only looking at coincidences here. On the x-axis is the difference in frequency of the two photons. I have three different lines here corresponding to three different relative delays. You see a interference pattern that changes with its fringe spacing as we vary the delay. If we do the same thing, but measure at a range of delays and then stack them vertically on top of each other, we get plots that look like this. Now a single vertical slice of this plot here corresponds to the Ou-Mandel pattern that I showed earlier, where you have a fixed difference in photon frequencies. You scan the delay and you see this V pattern. Now we do the same thing with two samples. One of them contains a solvent on its own. The other has the same solvent with a bit of an infrared absorbing dye in it. By comparing the two spectra, we can determine what the absolute absorption and phase spectrum of the dye are. For the absorption spectrum, we do something very similar to Klitschko. We just compare the number of coincidence counts to single counts. You can see that there's a band here about a quarter of the way over from the center that has a decreased intensity when we add this dye. There's also a symmetric band on the other side that has the same decrease in intensity. That's because after the beam splitter, we've erased this path distinguishability. If we detect a pair of photons, we cannot tell whether it was, say, lambda 1 that passed through the sample or lambda 2. And so these two outcomes show up the same way in our interference pattern. For the phase shift, we just look at each column here, fit it to a sinusoid, extract the phase, pretty standard. This is the spectra that we get for this absorbing dye that we've measured. I've plotted it here compared to the same spectrum for the same dye measured by a commercial spectrometer. On the bottom there, I show the phase response that we get compared to the phase response as inferred from chromochromic relations. We get qualitative agreement in both of the spectra. You'll notice that there are systematic errors on these little shoulders in the absorption spectra, and there's similar features in the phase spectra. That's due to an experimental limitation of our current setup. When we detect our photons, we couple them into single mode fibers before they go to the detector. That lets us get a good interference pattern by sort of rejecting photons that are not aligned properly and would not have interfered well. However, because we're using broadband SPDC, the light that emerges from the crystal has very strong spatial spectral correlations. The reason why this matters is that when we introduce different samples to our interferometer, the glass in the cuvette has a slight wedge to it. This deflects the beam left and right as we switch from one sample to another. This deflection changes essentially the spectrum of the probe light that we're looking at our sample with. And so it leads to these differences. We see the same thing in the single spectra. So it's something that in principle could be calibrated out. Alternatively, it's probably better just to avoid the use of these single mode fibers or to engineer your source a bit better. I should talk a little bit about what the prospect is here for a quantum advantage in this type of spectroscopy, since that's where I started. I've plotted two plots of the Fisher information here. The Fisher information, for people that don't work in metrology, is a quantity that tells you how well you can go from measured data to a estimate of a certain parameter. If you remember Aaron's talk yesterday, that's the last step in this grand scheme of metrology that he showed. So larger Fisher information means more precision. For absorption here, if you look, the red curve is the Fisher information for Klitschko's measurement. The blue curve is the Fisher information for this Ou-Mandel interferometry. In the limit of low losses, we find that Ou-Mandel has essentially the same Fisher information as Klitschko's method. To be clear, the Klitschko and other reference plots that I have here are exact calculations of the Fisher information. For the Ou-Mandel case, it's only a lower bound on the Fisher information, so it might be a bit pessimistic, but we do expect them to converge to the true value in the limit of low losses. When we turn to phase, you also see that spectrally resolved Ou-Mandel is quite sensitive to losses. In this case, you don't see a quantum advantage in the limit of low losses. It's hard to see from this plot because all of the low loss lines overlap at this green line here. But in this case, spectrally resolved Ou-Mandel saturates the classical shot noise limit. So we get a quantum advantage in absorption because of this heralding. We don't expect a quantum advantage for phase based on these calculations. However, this is quite promising. It means that if you have a feature in your spectrum, such as an absorption or a resonance absorption, that will show up with a signal in both amplitude and phase. If you can do separate measurements using this type of spectroscopy, you get independent information about this resonance feature from the two types of spectra. And by combining them, you can potentially get better precision in identifying a resonance wavelength, for instance, than you would get from Klitschko alone. So in conclusion, we've done a proof of principle demonstration of this absorption and phase spectroscopy using this Ou-Mandel. If you want to make this into a practical spectroscopy, you need to address this issue with single mode fibers or engineer your SPDC to not have these spatial spectral correlations. You also need very low efficiency, very low loss detectors and optics so that you can get to this quantum advantage regime. We're taking this in a couple different directions now with follow-up experiments. One of them tries to replicate the same results without the use of any fibers. We just go straight from our source onto a detector. In the other one, we're trying to integrate this into a pump probe setup. Essentially, you have synchronized pulses that drive the parametric down conversion and also excite the sample. And by varying the time delay between these two, you can step through what the temporal response of an excited sample are. With that, I'd like to acknowledge the many other researchers that worked on this project. In particular, Andrew Propp at the top left there is the other main experimentalist that worked on this project with me. Yeah, thank you for your attention.